right, so just for your information, this is the second time I've recorded this lecture. The first file got corrupted. So I'm going to do something I don't do very often. I'm just going to use previously written out notes. So far when we've been doing circuits, we have concentrated on them from a microscopic electron point of view, which has the downside that electrons are hard to measure. I mean, this is fundamentally what's happening, but difficult. However, conventional current I is very easy to measure. And so at this point, we're going to be making a switch from thinking about it mostly in terms of electrons, in terms of conventional current. But don't forget those microscopic roots. I mean, that is the fundamental physics of how a current works. And if you are solving different problems, going back to conceptually what's going on is actually a really good way to solve these types of problems. So moving on, we could look at conductivity. So this is how likely a material is to allow current to run through it. And we're going to look at this from a material perspective. So we know conventional current I is equal to Q N A V bar. And V bar is equal to UE, so we can substitute that in and say conventional current is equal to Q N A U E. So let's look at the different features. So we know Q is the absolute value of the charge carrier, N is the number density of the charge carrier. And remember, if it's a metal circuit, it is probably an electron. However, ionic solutions can also conduct current, and they might be having a current with positive ions or ions that are multiples of a charge. So N more specifically is that number density. A is the cross-sectional area of the wire, filament, etc., or whatever it is that you are conducting this current through. E is the electric field, and U is charge mobility. Now you've noticed I've circled some of these in red. These are all properties of the material. The material determines what the charge carrier is. The material has a specific number density of charge carriers. U is the charge mobility. That is specific to that material and the temperature and the other conditions. And A is a geometry that you predetermine by how you're constructing this. The really big fundamental physics part of this is that electric field. And how that electric field is going to dictate the current is completely dependent on what properties the material has. All right, so let's group the properties together. And what we want to go for is something called current density. So if we take I divided by A, so then we have Q and U, which are specific material properties that are immutable, and then area, which you can determine yourself, and E you can apply. And so you get current density J, which is equal to I divided by A, which is equal to Q and UE, or something known as sigma E, where sigma is equal to Q and U. So J is actually a really important concept. It's current density. The units are amps per meter squared. Sigma is the conductivity, and that's the charge carrier times the number density times the electron mobility. So these are the unique material properties, also with some conditions thrown in there. What I mean by conditions is temperature impacts electron mobility. And the vector J is the vector pointing in the direction of conventional current I. And we typically write J is equal to sigma E. And as J is also equal to current divided by cross-sectional area, the units are amp per meter squared. And basically, what conductivity is it's determining what E is going to do to any material in terms of running a current through it. So a higher conductivity is going to do different things than a lower conductivity. Okay, so let's look at conductivity in something with two charge carriers. So salt water has positive ions, the sodium chloride, and positive ions, the sodium, negative ions from the chloride. And if you fill a container of salt water and you run a current through it, the chloride ions are going to go opposite the direction of the field, and the sodium ions are going to go in the direction of the field. And because you now have a moving charge, you now have a current. So Breaking this down, for the positive charges, the sodium plus, we're going to call them Q1. Conventional current is equal to Q1N1AV1. And for our negative charges, Q minus, this is from the chloride ion, we're going to call it Q2. It has charge minus E. And current is equal to the absolute value of Q2N2AV2. So remember that because a negatively charged particle also goes the opposite direction, the value for conventional current is the same. So minus Q going in the minus V bar direction is the same as positive Q going in the positive V bar direction. So this is why that convention didn't change even after we learned that it was actually the negative charges moving, because you can still do the same physics. Again, not my judgment call, but that's what happened. So one thing to note with these mobilities probably differ because larger ions have less mobility, typically, which makes sense. So you want to make sure that you're reading these questions carefully and looking for all of the different values. But anyways, going back to our salt water. So if you want to look at the total current in this salt water, you're going to need to sum together all of the current contributions. You're going to have positive charges going one way, negative charges going the other way. And remember, current is just charge passing through a cross-sectional area per second. It doesn't matter which direction it's going. So if you have these three charged particles passing through at the same time, we have 1 plus and 2 negatives, then you would have 3 charges per second. So you would sum these two together for your conventional current I. I is equal to Q1N1AV1 plus Q2N2AV2. And then just a note, I said that before, but Q could be a multiple of E. So if you had a zinc plus ion, Q would be equal to 2E. But so just again, make sure you're reading the problems carefully. All right, so ending that little aside, we could then express current density in terms of conductivity. So J is equal to I over A, which is equal to Q1NU1E plus Q2N2U2E, which is equal to sigma E. And sigma is equal to the sum of the conductivities of both of those charge carriers. So that's Q1N1U1 plus Q2N2U2.